Okay, so today will be the officially last day of our class. Yeah, next week we are going to have the final exam. But I think there are some supplement that I need to, I think, just to give just additional information, not really going into our final. So after final exam, I will prepare some videos that hopefully can just maybe like a short video that is summarize the rest of the chapter 15, okay, that I haven't yet explained in class. I will just make a short summary, and if for example in the future you need to have some references, like because we still have the surface area triple integrals that we haven't yet explored, so I will just give you some information about that. And yeah, hopefully if you need some references, I think I will just keep that video and then just give the link to you so you can watch when you need to know the further step. But essentially for chapter 15, what we have done in class, that is basically the fundamental parts. So the double integral over general regions, the polar coordinates, the conversion, and then the Jacobian transformations, they are basically, I think, the necessary one that we need. And the rest of it, like the triple integrals and conversions to, we call the cylindrical coordinates, and the spherical coordinates, that is I think additional information that perhaps you need to know if you are maybe in the future in other course that related to calculus or advanced mathematics in general. I think you can just watch the videos, okay, and not include in our exam. So for today's class, I'm preparing some questions. So I think let's start with let's just try from chapter 14. I think yesterday we already learned about this, but let me check again. Okay, let's try. Let me give you questions. I'll consider. So we have functions that at 0, 0, it will be equal to 0, but at other points, it will equal to the function xy. Okay. And then let g equal partial x of the functions. And then the question is directional derivative of g at 0, 0 in direction vector u, which is equal to, okay, it has some options. Let me just give you options here so that you can have maybe have predictions which the answer. So a 0, b square root of 2 over 2, c negative square root 2 over 2, and d square root of 2. Okay, this is the first one. So you need to understand the question, which part that is going to be our concern. So we are given the function of two variables x, y. And then we have another function called g, which is the partial derivative of x from this f, right? Okay. So I hope you understand which one of this going to refer. Okay. So it's going to be directional derivative of this g. So the partial fx. Okay, so let's try first. Let me give you maybe a couple perhaps maybe 4 or 5 minutes. So you need to calculate first the partial, okay? And it's a little bit quite long, but actually it's simple, like just like calculation in calculus 1, okay? But just think y is like a number, like a constant. We focus on deriving on the x, right? Deriving on the x. Okay. Actually, the question can be also, I'll give you the option 5. Maybe it doesn't exist, but it should be exist, and you can prove it. Okay, let me refresh our chapter 14. So let me write here some definitions that I believe should be a fundamental and probably important. So directional derivative of f at point, let me just write at, let's say x 0, y 0 in direction of unit vector u is, this is the definition, by taking the limit as h, take 0, so f x 0 plus ha, y 0 plus hb, and minus, okay, and then divided by h, provided that limit is exists. Okay, this is the directional derivative that we are going to compute, okay, based on the questions. But first, before we arrive at this limit, we need to calculate the partials. So since the partial, okay, so let me write again, let me put here, let me copy and write here. So since we have this f, right, and we are going to compute the partial x, okay, then we are going to use the quotient rule, and this will be very long. Okay, we're good for exercise, not good for exam, right? Or maybe good, no? But I think for exercise, I think it's quite okay. So I think I will just write this as xy, or let me write just to make sure that I write all the components correctly. Okay, so first is we need to derive that. So 3x squared, or 3x squared y, right, minus y cubed, and then multiply with this. Okay, I think I will move a little bit to the left for this part. Okay, and then minus 2x, and then x cubed y minus xy cubed. Oh, too long. Okay, right? What next? I think I will just multiply first and see what it looks like. So 3x 4y minus y 5, right? Okay. And then this part here is negative 2x 4y and plus 2x squared y cubed. Okay, I think we can take this out, right? 3 minus 2 is 1, right? So we take x5, x with power of 4, y minus y power of 5 plus 2x squared y cubed divided by this x squared plus y squared, right? Well, if you want, maybe take out y and then x4 plus, I think, do I have some mistake here? Ah, correct. Let me erase first here. And I haven't completed this yet. Okay. I think let me just erase first here and then redo again. Ah, good. So yeah, that's why there is only 4. It should be more. Okay, good. And then that, and then plus 3x squared y squared, and then minus, now it's complete. 3x, oh, good, yeah, right? 3, oh, wait, this 4, this is correct, right? Wait, this one here, okay, 3x cubed. Okay, now correct, right? Okay. Now this will be 4 y plus 2x squared y cubed. Okay. Sounds still. This is still the same. And the second one will be what? 2 plus 2, right? Plus 4, right? And then minus y with power of 5. Okay, and then if we would like to factor out y, okay, so we have this. Okay, so let me check. So it's asking the rational derivative of g at 0, 0. So what does it mean? So we are going to input this. Okay, so first is taking the g 0, 0, right? So we are taking limit so this is taking the f0 plus h, and then taking the f0, 0, and then by taking the definitions, okay, you will see that it will going to be 0 over h, or it's going to be 0. Okay, but this is not. This is just to prove that we have the limit definition for the partials, not really the directional derivative. So by definition, so directional derivative limit. Now what we are going to do is we take directional derivative of, now it's g. Okay. So we take g, so we have g 0 plus, so here, okay, x0 plus ha, y0 plus hb, okay. So we just take that. So our a and b, what is our a and b? Is this, okay, these two. So we took these two inside. So it's quite long formulations. And then put another, okay, and then minus. Okay. Now we already have definition for f0, 0 based in what we have in the calculation here, that this is going to be 0. Okay. So, and our g00 is basically it's 0. So I think this is should be G, sorry, this should be G. Okay. So then what we have now is we are going to put all this square root 2 over 2. So put into our equation over there, or maybe over here. Okay, the same. Okay, so why we put the h squared 2 over 2. So let me write that. So I think I will write, let's take the limit. So whenever you have like really messy computation, like a big chunk, start by looking at the pattern and see if you can maybe classify each groups. Okay, do not mindlessly try to compute all together like you are doing in probably in elementary school. So don't do that. Okay, so do nicely and take your time, but do not really take too much time. Okay, so y, so let's write here. So this will be square root of 2 over 2 h, and then multiply with 1 over h. This is, I will move over h going to the left. So what we have on the right side is just this. Okay, just this formula here. So that formula is actually what we have in our G, right? In our G here. So let's plug in all. Let me write with green. So we are going to have square root of 2 over 2h with power of 4 plus 4, and then square root of 2 over 2h squared. I don't have space, so I think let me move this part, or maybe let me move all here, move to the new page. Sorry. So copy. Okay, and make it a little bit smaller. Okay, so plus 4, and then y is the same, and then minus square root of 2 over 2, and then I think it's nicely done, right? Okay, you can see how we could simplify it at the end. It seems like it will be very long and messy, but you can see some pattern can be cancelled, right? Okay, so what's next? Oh, this h can be cancelled. This can be cancelled. And then what else? This is 2 over 4. So 1 over 2h squared plus 1 over 2h squared. It will be h squared. So this will be h squared. And then what will be here? 4, and then the same. So this will be 1 over 4, 1 over 4, right? 1 over 4, h squared, right? And then cancel. So h squared, it's gone, all gone. H squared, oh yeah. Wait. Let me check. H squared, oh yeah. Let me check. Squared is 2 over 4 h. So okay, this is h squared and plus. It's h squared, h4, yeah, correct, h4. So this will be also h4, right? Because squared, yeah, same conclusions, okay? Yeah, but that's more correct. Okay, so all here will be gone, right? So the result is sure. So basically, you're going to see that. Some questions, although you know the definitions or practical implication from the directional derivative, which is the practical implication is this, right? The gradient factor, and then multiply with the unit factor, unit factor u, or maybe this is unit factor u, right? But sometimes take back to definitions maybe can solve problems, especially for conditional functions. The conditional functions is when you have this. Let me write for a while here. Conditional function is when you have this and you have this. This is what we call conditional function. Sometimes we are using the like two paths, like one way take 0 if maybe some points when you plug in some points, and in other points this will be this function, or maybe we have more than one functions. Maybe not here, maybe in other points it gets another functions or equations. If that's happened, the safest way to define all this is through the limit, okay? Because that is basically the fundamental part of the partial derivative. Okay? So always remember, whenever you see any derivative problems, if you are not able to solve practically, then you need to go back to the definition. Go back to the definition. Back to the definition means you're going to back to this limit. Okay? This limit. So sometimes maybe the question is not really direct. Okay? This part is practical implications. What we are doing when we have like a direct question. You know the functions, you know the unit vector, and it's just asking the partial derivative. Just compute, like just basically regular computations. But this type of questions, like we did here, this is forcing you to go back to the definitions of the partial derivative, which is going to have a limit. Okay, I think. Okay, perhaps this one. Okay, just to. Okay, that's the next one. Yeah, yeah. Yes. And then find the extreme value, and then check the points. Yeah, at the end, you can classify, like, you can check the d, right? D, and then the partial xx, whether it's positive, negative, and then you can mention which is whether it's maximum or minimum, or maybe saddle points.
That would be the complete exercise.
Yes, yes. Maybe you can just take partials equaling to 0, find some equations, and then substitute perhaps, or eliminations, and find the points. So that will be the extreme values, and then check the second partial derivative. Yeah. You can write all partials first, and then equaling to 0 for the first partial. Okay, perhaps let me help you. So finding the critical points is taking the partials. You can write directly like the gradient f. So you can write both inside here if you want to go into or in just one line. So perhaps this is partial x on the left, 6x squared plus 2y squared minus 6x. And then the partial y is 4xy plus 2y, right? This is partial x, this is partial y. And then we need to find when this is equal to 0, right? So taking the 6x squared plus 2y squared minus x equaling to 0, and then taking the 4xy plus 2y equaling to 0. I think we can take this, take 3x squared plus y squared minus 3x, right? So we can take 3x and then x minus 1, right? And then plus y squared. This is equal to 0. And then the second equations, we get 2x plus 1, or this is 2xy plus y, right? So 2x plus 1y, right? So we get that from this part, y probably 0 and x is negative 1 over 2, right? And then taking these two, y and x, we go here. What will we get? So 3x squared, so xy, so when y is 0, this will be this, right? So x0 or x1, right? So let me rewrite this with different color. This is 0 and x1. When x is negative half, do we need this? X negative half? What will we get from here? We get imaginary number, so I think we can exclude this part. Okay, we can exclude, right? We can exclude this part. Okay, so we are only focused on this. So the critical points are 0, 0 and 1, 0. Okay, only two that is necessary in our computations. Okay, and then let me copy again this part, taking to the new page. So we take the D, right? D, or maybe we take 0, 0, 1, 0. Okay, we are going to continue later, but I will just write first all the necessary components. Okay, so let's continue just to finish off what we have. So check D for these 2 points, 0, 0 and 1, 0. So D for the first one is, so take 0 to all these components here. So the second partial, so this will be negative 6. And then multiply with 2, right? So it's should be negative, and then minus 0. So it's negative, right? So it's negative. And we can directly say that this is going to be saddle, right? Saddle point. And then the second point, 1, 0. So we put first, it's 6. It's also 6. And then minus 0. So it's going to be positive. And we need to check the partial xx or partial yy. So let's just check partial xx is positive, right? It's positive. So positive, positive. So this will be a local minimum. Okay, local minimum. Okay, or we can write like 0, 0 is saddle point. 1, 0 is local minimum. Okay, let me give you another questions. So let's move to double integral. Okay, so compute. I will give you directly 2 questions now. So 0, 4. Okay, so try that one. Okay, so these 2 questions is basically you need to observe more. Okay, so not all integration can be directly calculated, right, as we mentioned, right? So sometimes we need to manipulate the integrations. Okay? So perhaps if you look here, we are going to have the dy first, right? But it's having the over y, which it seems like it complicates our structure if we are going to force the integration. So the wise method for this one, for both of this, perhaps we are going to switch this. It becomes the SEY. Okay. So that means you need to know how exactly this area looks like. So perhaps sketching the area may be important, just to give visualizations on how the integration looks like. So this part here, from 0 to 4, which is the x, and then from square root of x to 2 for y, that's just described in a sketching, in sketch. Let's describe in a picture first. Okay. So let's say we take the x is from 0 to 4, and then y from square root of x 2, right? So what we need is first taking the graphs. So I think, let me take this 1, 2, 3, 4. Okay, so that's x equal 4. And then take 1 and 2 over there for the y. So let's make some dashed line just to make sure that this is our endpoints. Okay, and then we have y equal square root of x, or we say this is x equal y squared. We can say that. So in terms of this area, then we draw. This is our y equals square root of x, right? And then we need to, let me maybe define this. Or maybe this is going to be down here, okay? Because the one that we are looking for, okay? If you take, so this is I think really tricky, okay? So we are going to make 0 to 4 as a constant. Okay? So it's going to be moved over there. But then in y, it's going to start from here to y equal 2, right? So it's going to be this area. Agree? Can you see it? You need to understand first why exactly that area is our area. Okay. So we go from 0 to 4, and we go from this curve to y equal 2. Okay. So let's draw the line here, and then let's describe this as our area. This is actually our area from this. Okay. So from this y equal square root of x, y is this supposed to be okay. Okay, now we are going to switch. Now we are going to make y-axis as a constant. So of course we see 0 and 2, right? Okay. So we write first. Now we can see that let me write with green. So this is y and 2. And how about x? Where does it start? So we still want the same area. So if 0 to 2 is y, then x is this line here, right? Up until this curve, right? It's going to be that, right? So from x equals 0 to x equal y squared. Okay, do you get it? Do you get it? Okay. Okay, so let's write the formulations. So then this will be, so let me write the question is 0, 4 squared x2. This is sine x over y dy dx. This equal to, we switch to this. The inside is still the same. And now it's dx dy. And now it makes sense to integrate this, right? And we can treat y as a constant. It's a constant. So sine x will be negative cosine, and then multiply with the constant, right? So not yet it's complete, so we just need to solve the computations. So taking the 0, 2, and then multiply the inside integration here. So we get negative cosine x over y, and divided by 1 over y, right? And this will be input 0 to y squared, and this is dy. And then this will be, we can write this, I think we can write this like this, right? Okay, same. So we input y squared into x, so we get this is wrong, x over y, sorry. So y squared it's y, so negative y, or let me write a little bit below here, negative y cosine y, and then 0. Don't forget 0 for cosine, it's become 1, right? So negative 1, negative, it's going to be plus y dy. And how to solve this? You need to remember calculus 1 techniques if you forget. So let me give you tips. Techniques that's supposed to be, I think, frequently appear in calculus 2, substitutions, integration by parts, or just trigonometry using double angle formula. I think that's the most often. Okay? So you need to just keep remember that. Okay? So this you can take integration by parts. Okay? Take integration by parts. So remember, what's integration by parts is di. So we take the derivative on the left part, right? So take here, let's say y. This is y. So y cosine y, and then this will be 1. This will be integrated, become negative sine. Okay, and then take again, become 0. So it becomes 0. This will be integrated again, become cosine y, right? So take here. This will be what? Negative y sine y, and then minus cosine y, right? And then plug in 0 to 2, and don't forget we have plus or maybe let me write, this is going to be this, and then this will be plus. Don't forget we still have plus half square. Okay, this is going to be that. And then plug in 0 to 2.
Shouldn't 0 just sign y?
Hmm?
Shouldn't it be just sign y? This has been where the 7 is
Sine? What is the integration of cosine? Sine, right? Oh, yeah. Good. Right. And this will be negative. Oh, yeah. So, but the answer correct, right? The answer, unfortunately, the answer correct because we need to multiply with negative. Okay. If this happened in exam, you're lucky.
Yes.
Good job. Okay. So you can plug in -2 sine 2 minus cosine 2 plus 2, and then minus 0 minus 1 plus 0. So 2 plus 1, 3 minus 2 sine 2 minus cosine 2. Okay, integration by parts is used this way, faster. Okay, now let's try the second question. Do not be intimidated because it has like 2 regions. Just focus on what we are going to take. Okay, so first thing, focus on x and y, right? The range. Focus on the range. So this is y as a constant, right? So every time y is at the very end, that will be a constant. We have constant 1, 2, and 2, 4. So if you imagine a graph, it will have 2 regions that separated by this range. Range from 1 to 2 for y, and another y is from 2 to 4. Okay? And another region, or another range that we need is x. So we have this x equals square root of y, and x equals y, which is, this is just a parabolic and then line equation. Right? So I think we can draw it very, very simple. So we describe the equations. So first is taking the y-axis into 4 points. So from 1 and then 2. So this is all the importance point that is going to be expected, defining the area. Okay, and then draw the first is the line equation, which is y equal x. Okay. And then x equals square root of y, or this is just a normal y equal x squared. Okay, and then you can maybe, to make sure that this is correct, we can make sure that if it's equal to, this will be 4, right? So this will be there. And then we have, we have x equal 2. So I think I will just write line here, make it x equal 2, and then we take the parabola. So I think I need to make it bigger, but that's okay. So let's suppose that this is going to be the parabola. Okay. So the area is this one. Okay. So we have, okay, this is area 1, this is area 2, right? Okay. So this is from 1 to 2 and 2 to 4. So this 1 and 2. Maybe take a color here. And then with the similar principle, first you check integrations. If it's not make sense, perhaps you need to switch the dx dy. So that's what we are going to do now. And then we are going to make it into, from dx dy, make it into dy dx. And I think it's better, right? From 2 regions, we now have only 1. Okay. So we could see from here. Now we want dy dx. Okay, we want dy dx. So x is start from 1 here, 1, and then x starts until 2. Okay, 1 to 2. So x is from 1 to 2. So that's the constant. So x started from 1 to 2. And then what about y? This y equal x, right? And this x squared. Okay? So then what we have now, we can write 1, 2, x and x squared, and then write the inside integration. And not complete yet, we need to compute now. I think dy, there's no y inside, so you can just make it y and then plug in x squared minus x and then multiply with this. So we can take, this will be x squared minus x, multiply with cosine, like that. And perhaps you feel nervous, compute this. Remember, focus on the 3 integration if you need to calculate. If not, substitutions, integration by part, or just trigonometric. This is x cubed, x squared, but having over 3 over 2. This is x squared minus x. Can you see the patterns now? If you try to derive this, it will become this, right? Try to derive the inside here, x cubed, derive, become 3x squared, 3 cancel here, x squared, okay? X squared here, 2x, cancel 2, become minus x, okay? So take that as a substitution. So let's substitute the inside of the cosine. So take this as that, right? And so we could exchange the x as 1 over x squared minus x du. So we could cancel now, right? And then don't forget, if we change the x into u, then all the endpoints also, we need to do that as well. So when x equal 1, u will be 1 over 3 minus 1 over 2. 2 minus 3. 2 minus 3, negative. So negative 1 over 6. And when x is equal to, u will be 8 over 3 minus 4 over 2. Or we could write this is 2, so 6 over 3. So 2 over 3, right? So exchange this into negative 1 over 6, 2 over 3, and then cancel, and then cosine u du. And then simply we can exchange this, becomes sine 2 over 3 minus sine negative 1 over 6. And the sine negative 1 over 6 is negative, or we can just write this is just plus sine 1 over 6, right? Both are correct. Both are correct. Okay, any questions first? Any questions? Is this something that you can work on exam or not? Yeah, it is quite challenging. But the previous one, the critical points, I hope you can do that in the exam. That's pretty standard question. But this one and then the direction derivative one using limit definition, that I think quite challenging. Takes some time to work. Okay, I'm going to give you one more. Okay, one more question. Okay, one more question. Let R be the region on xy plane bounded by square with vertices so if okay, so it's giving you some double integral with some value over the right side, and it's asking the value of a, it is a. Okay, what should you use? Which method you are going to use? Any idea? Yes. So we are going to change the variable. Okay, Okay, so whenever you have something inside the integration, there may be some complication between x, y, okay, or usually the complication is either having this linear subtraction or addition, plus minus, or perhaps maybe y over x or xy multiplication or division is also can be done by changing of variables. The thing is, we need to know how to connect the xy into uv. So how to connect that? Usually you are given by these vertices, right? Or any other like constraint or something like that that you need to observe first. But since now we have the square, which means it will be just a constant. We are not having any. For example, if you have like parallelogram or any line that is not really defined by square or rectangle, it means that you need to at least to draw to see, okay, what kind of function that is bounded, okay, that is the boundary. So because it's square, so we can just take the points. Okay, take the points, and it seems that it's x plus y and x minus y. It's just our substitution for u and v, right? Okay, so this is, I think, if you read some of the exercises, or if you have the textbook and you read some question on the textbook, this is some of the question that is quite obvious. That whenever you see this one, then immediately you need to go to change this. X plus y becomes one variable, and x minus 1 will become another variable. So suppose that this is u or v, and this is v. Okay. Okay, and then let's try to find the Jacobian, right? The Jacobian formulations, right? So we take, let u is x plus y, v is x minus y. And then if you want, you can try to define, so when it's 1, 0, u is 1, or maybe this is xy. Let me write, this is xy, this is uv. Okay, I think that's okay. So this will be 1, and xy, it will be -1, right? And then what else? 1, 2, this is 3, this is -1, and then 2, 1, this is another 3, this is 1, and then 1, 0, this is 1, this is 1. So u will be from 1 to 3, v is -1 to 1, right? And then as usual, we are going to make x in terms of u and v, and y also in terms of u and v. So we need to eliminate this. I think we can plus. So 2x is u plus v. So x is half u plus half v. And y is u minus v, right? Half u minus half v. And take the Jacobian. So this will be half, 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 negative. And it's absolute value, remember it's absolute value. So we have -1/4, -1/4. This is going to be 2/4 or just half. And then we write again, let me write again the formulations. This is x plus y squared, and then sine squared x minus y. That's right, dA. And then change to uv. So x plus y is u squared, sine squared v, and then Jacobian is half, so half. And then let's say, since we have constant for u and v, so we can write dv du or du dv, the same. So let's just write du dv. So v is here, Okay, now we have sine squared, we have u squared. I think we can separate by the Fubini theorem. Okay, remember? So whenever you have these endpoints all constant, and you can separate this become two functions, you can separate. Okay? So it's going to be, this is for the v, and then we write half in the front. And then we have 1, 3, u squared, u. Okay. And remember, you have trigonometric sine squared, take double angle. So only 3 substitutions, integration by parts, double angle from 1. Okay. And that's the most frequently used. Okay, just my tips. Okay, double angle. We write double angle formula. Okay. So we have sine, then we have this is going to be half minus half cosine 2v, right? So we take the integrations. It's going to be half v minus cosine becomes sine 2v divided by 2 and multiply by 2 and divide by 4, right? And then multiply with, I think we can just multiply this. This is half minus sine 2 over 4 and minus negative half I'm writing a little bit messy here, sorry. Three cubed is what? 27. 27, 26, right? 26 over 3. This is going to be 1, right? 1 minus sine 2 over 4 negative sine. This is negative, so this is plus, right? Plus sine 2 over 4. So this will be what? Sine 2 over 2, right? And then multiply with half. So this will be 13 over 6. Over 3. Yeah, I think just 1 minus sine 2 over 2, right? Oh, yeah. Why I multiply again? Okay, good. So I think we just finished this, right? Out there. Okay. of that. Okay, any questions? Okay. If I have time within this week, I can add maybe additional video. And for those of you who are asking like the answer key for the last exercise, I'm not really having it. Unless I have time to work on that exercise and prepare for you, because I need to also prepare for another exam as well. But if I finish and I can give you more additional exercise or videos, solution videos, I think I will prepare maybe 2 or 3 questions. So I'll see you on finals. Don't forget to study, okay? And I think whenever you take courses, before you take, or maybe when you read the information, or maybe when you sit in at the first time, usually the professor gives you some highlight of the lectures. If you think that you need to study hard, you need to know yourself, okay? You need to know like what the thing that you know, what you think you like, and all the things that is going to be your boundary. You need to know, okay? Because you are already adults now. So, for example, between chapter 12 to chapter 15, I think some parts, ideally, you need to understand everything, but I think no, right? So you need to maximize the one thing that you are good at. So I believe if you take some time to optimize yourself, you could do better, okay? A little bit feedback. It's not a question, just a survey. Just a survey. So don't worry about that. Just a quick survey. So go to the left part there, or just go to the website and enter in the code 14522744. Just a short survey, and hopefully every year I can improve my courses. Okay. Fundamental courses like calculus, chemistry, physics, it's identical to be a little bit boring, right? Because it's fundamental courses that has certain chapters that need to be completed. So I need to think like, what improvement should I make in the future? Okay, let's go start. Okay, course feedback survey. Okay. Oh, some already did. Okay, good. Okay, when you enter second year, third year, some courses will using some calculus, and then you will maybe realize, why I didn't study this. Okay, and then last part is ID. Okay, if you're done, then finish.